Assalamu alaikum, dear students. Today's lecture is the 6th lecture of numerical analysis. In this lecture, I will be talking about the MATLAB code for the construction of the divided differences and differences table. We discussed in the previous lectures that how we can construct the divided differences table and differences table. So if the target is to write the computer code, the MATLAB code, to construct these differences table, so today's lecture is related with that one. Let's assume I have a function f of x is equal to x squared plus x plus 1, and I'm generating data for this function. So definitely I should know about the values of xi's. But for the function f of x is equal to x squared plus x plus 1, if you remember, I told you in the class that you can write this function in your main program also, but if not, so you can define a function for it. This is function. I use this divided difference. So this is just the matter of notation. You can use any notation you like, and this is again, this is the notation I'm using for divided differences. You can use any notation you like, and this is the variable, and you will be sending information about this text to this file. Then I define that this d differences is defined by x squared plus x plus 1, exactly like this function. What you have to do when you write this function file, then you have to save by this name, d underscore diff.m, and this file should be there in your directory which you are using. This is the function file I constructed. This is the command. I'm asking the MATLAB to clarify all the variables defined. If already the values are defined, so clear them. So it will clear, and we start from the scratch. I having 5 number points starting from 1. Step size is 0.3. It means that according to this information, I have the data points are 1, 1.3, 1.6, 1.9, and 2.2. So these are the initial informations I provided to the MATLAB. Now I want to generate xi, so for that I need a loop. I will say I start from 1 and reach up to 5 because I need 5 points. As usual, we are defining xi is equal to x naught plus I minus 1 and to h, so I just use that formula and then enter this loop. This small loop of 3 lines gives me when I is equal, it will take I is equal to 1 and will go up to n, when n is equal to 5 in your case. So it will take x1 is equal to x naught plus 0. X naught is 1, so you are getting x1 is equal to 1. We'll take I is equal to 2. I is equal to 2, x2 is equal to x naught plus h. X naught plus h is 1.3. So this is a 1.3 which you will get. I is equal to 3. x3 is equal to x naught plus 2h, which will give you 1.6. And I is equal to up to I is equal to 4. x4 is equal to x naught plus 3 multiplied by 0.3, which is 1.9 overall. So 1.3 or 1.9 you are getting. And finally, when n is equal to 5, so it will say x5 is equal to x naught plus 4 multiplied by h, and that gives you 2.2. So this small loop gives you these data points. Now I have data points, function I have. Let's find out the values of the function at these data points. How to calculate f of xi with the help of MATLAB code. So let's define, this is the target. F of x1 is equal to f of 1, f of x2 is f of 1.3, f of x3 is equal to f of 1.6, f of x4 is equal to f of 1.9, f of x5 is equal to f of 2.2. 2. This is the target to find out. So I am defining another loop. I starting from 1. I starting from 1 reaches up to 5. Remember, this time I stored the values of the function in capital G. What this loop will be doing, I have to end this loop again. I is equal to 1 G of 1. It will send x is equal to x1 to the function file and will replace this x by x1. And x1 in your case is 1. And will compute value of the function at x is equal to x1. And will store that in G1. Similarly, I is equal to 2. G of 2 is equal to, will send x is equal to x2. x2 is 1.3 to this file. Will replace this x by 1.3 and will give you the value and will store that in G of 2. And similarly, I is equal to 3. G of 3 is equal to x3. x3 is 1.6. So it will replace x by 1.6 and will get the value. Similarly, I is equal to 4. x4 is equal to 1.9. Will send x is equal to 1.9 to this function file and will save that value in G4. And finally, when n is equal to 5, G5 will send x5. x5 is 2.2 to this function file and will get the value from there and will store in G5. And G5 will be f of 2.2. So this small loop generates the values of the function at the data points. So it's I think it's very clear. Now let's assume now the target is the construction of this divided differences table. You know that these are xi's. These are f of xi's. We generated them and replace f of x1 by g of 1, f of x2 by g of 2, f of x3 by g of 3, f of x4 by g of 4, and f of x5 by g of 5 in the previous loop. I use notation. I deal with this table as a matrix. This corresponds to the first column, correspond to the second column, correspond to the third column, correspond to the fourth column, and this correspond to the fifth column. First row, second row, third row, fourth row, fifth row. First row, second row, third row, fourth row. First row, second row, third row. First row, second row, third row. You know that this definition is equal to f of x1, x2 is equal to f of x2 minus f of x1 divided by x2 minus x1. And similarly, this value is equal to f of x3 minus f of x2 divided by x3 minus x2. In other words, this value minus this value divided by x3 minus x2 and so on. Similarly, this value is f of x2 x3 minus f of x1 x2, this value minus this value divided by x3 minus x1. x3 minus x1 is you already know. This means f of x1, x2, x3, x4. And this means f of x1, x2, x3, x4, x5. Because of the space I use this. So I will be generating these entries and you know the meaning of these entries. So let us generate this table. You can see this J I'm using for the column starting from 1, 2, 3, 4 and 5. That's the reason I'm saying J starting from 1 and reaches up to N. For the rows, I define this one. Why this is different from G? Because you can see here in this column we are having 5 rows. In this column we are having 4 rows. In this column we are having 3 rows. There are 2 rows and there is single row. As the value of J is increasing, the number of rows are decreasing by 1. That's the reason I have written I starting from 1 up to this quantity. When j is equal to 1, so this is the column we are using. J is equal to 1, so this portion will be 0, and I starting from 1 up to n. So you can see I starting from 1 up to 5. J is equal to 2, second column. J is equal to 2. 2 minus 1 is 1. So n minus 1. 5 minus 1 is 4. And you can see there are 4 rows. When j is equal to 3, j is equal to 3. 3 minus 1 is 2. N minus 2 is 3. 5 minus 2 is 3, and you can see there are 3 rows. When j is equal to 4, 4 minus 1 is 3, 5 minus 3 is 2, and you can see there are 2 rows. And similarly, when n is equal to 5, 5 minus 1 is 4, so 5 minus 4 is 1, so you can see there is just a single row. That's the reason I have written I in this form. Let's generate the entries. Now if you look at this column, these entries are the same as values of the function at xi. So that's the reason I am putting a restriction if the value of j is equal to 1. Double equality, remember this is using for equality in MATLAB. If you are using a single equality, it will not work. So be careful about this one. I am saying when j is equal to 1, generate this column for me. So f of 1, 1 is g of 1. G of 1 is f of x1. F of 2, 1 is equal to g of 2. G of 2 is equal to f of x2. F of 3, 1 is equal to g of 3. G of 3 is equal to f of x3. You can see here. F of 4, 1 is equal to g of 4, and g of 4 is value of the function at x is equal to x4. And similarly, f of 5, 1 is equal to g of 5, and g of 5 is equal to f of x5. Fj is equal to 1, so your MATLAB will use this calculation. Otherwise, I say else. If j is not equal to 1, then go for this formula. So when j is equal to not equal to 1, it will skip this portion and will come to this one. For example, if j is equal to 2, j is equal to 2, I starting from 1 up to 4 now. From 1 up to 4. That's clear from here. 1, 2. F of 1, 2 is equal to f of 2, 1, which is this value, minus f of 1, 1, which is this value, divided by I plus j. 3 minus 1 is 2, x2, which is this value, minus x of 1, which is this value. So you can see in this case that you got this value. And similarly, you can proceed further. When j is equal to 2, for example, it will take I is equal to 1. You got the value. I is equal to 2. So this will give you 2, 2. F of 2, 2 is equal to f of 3, 1 minus f of 2, 1. I is equal to j is equal to 2. So remember, I am generating this column. I is equal to 1. I discussed when I is equal to 2. I am looking for this value. This value is equal to f of 3, 1, which is this value, minus f of 2, 1, which is this value, divided by I plus j is 4 minus 1 is x3 minus x2, x3 minus x2, which is the definition of the divided differences. And finally, when it reached I is equal to 4, so this is the target value. 4, 2. This will be 4 plus 1, 5. 5, 1 minus f of 4, 1. F of 5, 1 minus f of 4, 1 divided by x 6 minus 1 is 5, x5 minus x4. x5 minus x4. So you can see that it generates the second column for you when j is equal to 2. This process will continue. When j is equal to 3 now, this condition is not satisfied, it will come to this one. J is equal to 3. I is starting from 1 and reaches up to 3 now, because 3 minus 1 is 2, 5 minus 2 is 3, so you can see up to 3. Let's come to this value. F of 1, 3. This value f of 2, 2. F of 2, 2 minus f of 1, 2, which is this value, divided by x of I is 1. So this is 4 minus 1 is 3. x3 minus x1. x3 minus x1, which you know about the definition of the divided differences. And this process will continue until j is equal to n. J is equal to 5. I will be starting from 1 and reaches up to, this is 4. 5 minus 4 is 1. Starting from 1 up to 1. Starting from 1 up to 1. And it will give you f of 1, 5 is equal to f of 2, 4 minus f of 1, 4, f of 2, 4 minus f of 1, 4 divided by I is 1, j is equal to 5. So 6 minus 1 is 5. x5 minus x1. x5 minus x1, and this completes your. Now you have started this f. We need to end it. We started this far, so we have to end this far. We started this far, we have to end this far. Now you can see that this is a loop containing 1, 2, 3, 4, 5, 6, 7, 8, 9 lines, and it constructs this complete divided differences table for you. I think it will be clear. What I will be suggesting, I am suggesting construct this divided differences table manually and then apply the code. You saw in the first loop we generated these data points. In the second loop we generated these data points, values of the function, and in this loop we constructed this complete table. So you can see that this line generates the first column for you, and this line generates rest of the columns for you. And if you look at your table, as we are increasing the values of j, the number of rows are decreasing by 1. Let us come to the other case. This is related to the differences table. Idea is the same. The same notation I am using. You have to generate these entries. This is exactly the same as the first loop of the divided differences table. This is exactly the same as the second loop of the divided differences table, so I am not repeating them again. I will be going for the construction of these rest of the entries. Let's go for a loop. Let's generate the differences. What is the difference between the previous and this one? The difference is this difference. I don't need the division. This delta f of x1 is equal to f of x2 minus f of x1. Yeah, this minus this one. Delta f of x2 is equal to this f of x3 minus f of x2, this minus this one. Delta f of x3 is equal to this minus this one. And similarly, delta f of x4 is equal to this value minus that value. So you can see the rest of the thing will be the same, but here we don't have any kind of division. Similarly, if we come to this value minus this value. This value is equal to this value minus this value. This value is equal to this minus this. And similarly, delta cube f of x1 is equal to delta square f of x2 minus delta square f of x1. And finally, delta 4 f of x1 is equal to delta cube f of x2 minus delta cube f of x1. So you can see there is no division, as we discussed in the previous lecture. So let us generate a loop. Again, you can see j starting from 1 and reaches up to 5. You saw in the previous case that I use j for the columns and I for the rows. The same idea. As you are moving in forward direction, number of rows are decreasing. So I explained in the previous loops that why I'm taking I starting from 1 up to n minus j minus 1. J is equal to 1. The idea is the same, is that of the divided difference. Okay, these values are equal to values of the function. I put this restriction. This is the same as previous. Otherwise, use this formula now. You can see it's the same as before, but there is no division by xi's. Computer will take j is equal to 1 and will say I starting from 1 up to n. Since j is equal to 1, it will use this value. F of 1 is g1, f of 2 is g2, f of 3 is g3, f of 4 is g4, and f of 5 is g5. And we computed values of the function in the second loop of the divided differences. If j is not equal to, for example, j is equal to 2, it will come to I starting from 1 up to 4 now. What it will be doing? 1, 2 is equal to 2, 1 minus f of 1, 1. Of 2, 1 minus f of 1, 1. That gives you f of 1, 2. This is the difference formula if you remember. Similarly, if we are coming for this one, I is equal to 2. 2, 2 is equal to f of 3, 1 minus f of 2, 1. F of 3, 1 minus f of 2, 1. And this will continue until j is equal to n. J is equal to n, so this will be 4. 5 minus 4 is 1. I starting from 1 up to 1. This condition is not satisfied. Will be switched to this condition. This will give you 1, 5. So this is 2, 4 minus f of 1, 4. This value minus this value gives you this value. N for f, and for second for, and n for the first for. This is the loop which generates the differences table for you. So you saw in this case, you have to generate these entries using the first loop of the divided differences portion, second loop to find out values of the function, and this is the third loop which will generate this table for you, which is the table of differences. Now let's come to another case, Hermite interpolation. In case of Hermite interpolation, you saw that the rest of the things are the same. Changes are only in the first divided differences column. and also we need the derivative of the function. So what we are doing, I'm considering a case. This is the function file. The same as in previous case. This is a function. Again, you have to save this function file with this name .m. The same as we discussed in the previous case. This is the function for derivative of the function. So you can see, if I take derivative of this function, this is 2x plus 1. You can see this is 2x plus 1. So I define another function which is related to the derivative, and remember you have to save with der.m in the main directory, and x is the variable like the function file. You have to send information about x to this function file, and that will compute the derivative for you. Let's assume this is the target. I have data points 1, 1.3, 1.6, values of the function, derivatives of the function at the data points. Function is here. If you send x is equal to 1, it will compute this value for you. X is equal to 1.3 to this function file, it will give you this value. X is equal to 1.6, it will give you this value. And when you send x is equal to 1.0 to this function file, it will give you derivative at 1.0. X is equal to 1.3 to this function file, it will give you f prime at 1.3. And if you send x is equal to 1.6 to this function file, it will give you value of the derivative of the function at 1.6. This is the target. Now let's generate these entries. It's similar to the previous two cases. This is a loop. X naught is equal to 1. This is the value. H is 0.3. You can see this is the step size. N is equal to 3. It depends upon you what are the number of data points. This N represents number of data points. Xi is equal to x naught plus I minus 1 into h. That's the formula which we are always using in numerical analysis. MATLAB will take I is equal to 1. X1 is equal to x naught is 1. If you remember, I told you that if this index is 0 or non-negative, MATLAB will not accept that. That's the reason I started this from 1. I is equal to 2, x2 is equal to x naught plus h, which is 1.3. This is the value you are getting. I is equal to 3, x3 is equal to x naught plus 2 into h, which is 1.6. This is the value which you will be getting from this loop. So this small loop generates these data points for you. If you are increasing the value of n, these data points will be increasing accordingly. I have just taken a small example so that the thing becomes clear to you. Now the next target is to find out values of the function and derivative at xi's. So let's see that what we are doing in this case. The target is to find out a value of the function at these 3 points, in other words, to generate this column, and derivatives of the function at data points to generate the third column. And these are the values. I told you we defined the function file. So this is a diff. This is function. When I is equal to 1, you are sending x1 to this function file. So replace x by x1. In your case, this is 1. So it will generate f of 1 for you and will store that in small g of 1. This is the value it will generate for you. I is equal to 2, G2 is equal to X. It will send X is equal to X2. X2 is 1.3 to this function file, and will get the value for you. F of 1.3 will store that in G of 2. And similarly, I is equal to 3, so it will send X3 to this file and will save it for you as F of 1.6. So this line generated this column for you. In other words, this column of your data. Similarly, if you come to this line, I just denoted this by DG. It's totally up to you, whatever the notation you are using. I'm sending, taking I is equal to 1, so x1 is 1. So you are calling this file. It will replace x by x1, which is 1, and will give you the value which you are storing is a dg of 1, value of the derivative at 1. Similarly, I is equal to 2, x2 is 1.3. If you send 1.3 to here, it will give you dg of 2, f prime at 1.3 is your x2. And similarly, when n is equal to 3, dg of 3 is, it will send x3 is 1.6 to this file and will give you the value, store the value is dg of 3, and that's the value of the function, the derivative of the function at 1.6. So this is the loop. Again, this is similar, but this is an extra line, and this is using for the computation of the derivative of the function. Remember, I use these notations, small g, dg. It's totally up to you, whatever the notation you are using. It will not create the problem. Now let's go far. If you remember, in case of Hermite interpolation, we are repeating the data. I have written x1 twice, x2 twice, x3 twice. Renumber them. Renumber them. So now if I write them twice, so the number of points will become double. So the 3 multiplied by 2 will be 6. And these are the values. So you can see these two values are the same, these two values are the same, and these two values are the same. And similarly, the derivatives at z1, z2 are the same, derivative at z3, z4 are the same, derivative at z5 and 6 is the same. So what will be the next target? Next target will be repeat the data points. So let's repeat the data points. I'm using this loop. Now I starting from 1 up to n. But you can see this is a 2i plus 1 I'm using for odd entries. 2i I'm using for even entries. Similarly over here and in this case also. So what the first two lines are doing, I is equal to 1. Now I told you I reassigned these values. So when I is equal to 1, so this is 2, I is equal to 1, so this is 0, z1 is equal to x1. Yes, I agree with that. I is equal to 2, so 2 minus 1, this is 2 plus 1. z3 is equal to x2. Yes, I agree with that. I is equal to 3, so 3 minus 1 is 4 plus 1, 5. x5 is equal to z5 is equal to x of 3. Yes, we agree with that. So we computed this value, and this value. Now let's come to the even. I is equal to 1. z2 is equal to x1. z2 is equal to x1. Yes, z2 is equal to x1. I is equal to 2. z4 is equal to x2. z4 is equal to x2, and you can see z4 is equal to x2. I is equal to 3, z6 is equal to x3, z6 is equal to x3, and you can see z6 is equal to x3. So I wrote every data point twice and then assign new variable to that. So these two lines will be doing this job for you. So this is the loop which gives you these information. Now let's come to the next loop. Always remember, when you are starting for, you have to end that for. I started for, I have to end this for. Now let's come to the construction of the second column. The construction of the second column. Again, I'm using the same argument, but this time I am denoting this by capital G, because small g was starting from 1 up to 3, G1, G2, G3. But now I need up to G6. I used different notation. It is up to you. Whatever the notation you are using, it will not create any problem. We'll take I is equal to 1. So this portion will be 0. Capital G of 1 is equal to small g of 1. Small g of 1 and small g of 1 is equal to f of x1. Similarly, I is equal to 2, so 2 minus 1. So this will be capital G of 3 is equal to G of 2. Capital G of 3 is equal to small g of 2 and small g of 2 is equal to f of x2. Similarly, I is equal to 3, so this will be 3 minus 1 is 2. So this is G of 5 is equal to G of 3. And G of 3, you know that was equal to f of x3. So you can see that this line generates for us this value, and this value. Now let's come to the next line. This is for E1. I is equal to 1 and G2. G2 is equal to G of 1. Yes, G2 is equal to f of x1, which we were looking for. I is equal to 2, G4 is equal to G of 2. G of 2 is equal to f of x2, which we were looking for. And similarly, when I is equal to 3, this is G6 is equal to G of 3. G6 is equal to G of 3, and you can see that this is the value of the function at x is equal to x3. So these two lines will generate this complete column for you. When you are increasing the value of n, it will go accordingly. Now let's come to this portion. In this case, the same argument. I is equal to 1, so capital D G of 1 is equal to small d G of 1. Small d G of 1, which is here. And small d G of 1 is equal to a prime at x is equal to x1. Similarly, I is equal to 2, capital D G of 3 is equal to small d G of 2. Small d G of 2 was equal to f prime of x2 if you look at the previous loop. And similarly, when I is equal to 3, capital D G of 5 is equal to small d G of 3, and small d G3 of 3 is prime at x3. So this line generates this entry, and this entry for you. Now let's come to the even one. When I is equal to 2, this is a capital D G of 2 is equal to small d G of 1, and small d G of 1 is equal to a prime at x1. I is equal to 2, this is a capital D G of 4 is equal to small d G of 2, and small d G of 2, you know that is a prime at x2. And similarly, when I is equal to 3, capital D G of 6 is equal to small d G of 3, and small d G of 3 is a prime of x3. So these two lines will generate the last column for you, which correspond to the derivatives of the function. These two lines will generate the second column for you, which correspond to value of the function. And this loop will generate these entries for you, which correspond to the repeated values of the data points. Hope this will be clear. Now let's come to the case to construct the divided differences table. You know that small changes are there, and the changes are in the first divided differences. If you have heard my lecture for Hermite interpolation, so I clarified it over there. I repeated the data points x1, x1, x2, x2, x3, x3. Similarly, f of x1, f of x1, f of x2, f of x2, f of x3, f of x3. But remember, f of x1 is equal to g of 1, f of x2 is equal to g of 2. F of x2 is equal to g of 3 as well as g of 4. F of x3 is equal to g of 5 as well as g of 6, which we generated. The change will occur in this column. How to generate these data points? We did that. This was clear from the previous loop. Similarly, we generated this one. Now let's generate the rest of the entries. Now you know that this time the value of g starting from 1 up to 2 and y, we doubled the numbers. N was 3, so now this is 6, and you can see 1, 2, 3, 4, 5, 6. So that's the reason I'm taking g starting from 1 up to 2n, which is different from the previous cases. The same, if you look at your table, 6 rows, 5 rows, 4 rows, 3 rows, 2 rows, and 1 row. So as we are progressing from left to right, the number of rows are decreasing by 1. Similar as the previous, but I replaced the total number of points this time as 2n, not n. That's the reason you can see this figure is different from the previous case. And similarly, this is different from the previous case. G is equal to 1. This generates this column for you. So I put the restriction J is equal to 1. Then these entries are equal to values of the function. J is equal to 1, it will come to this portion. Say f of 1 is equal to g of 1, and you know that g of 1 is equal to f of x1. I is equal to 2, 1, g of 2, 2, 1, g of 2, and g of 2 is equal to f of x1 again. f(3,1) is equal to g of 3, f(3,1) is equal to g of 3, which is equal to f of x2. And similarly, f of 4,1 is equal to g of 4, and g of 4 is equal to f of x2 again. So you can see this entry. And similarly, 5,1 is equal to g of 5, and g of 5 is equal to f of x3. And similarly, I is equal to 6, so 6,1 is equal to g of 6, and g of 6, you know that is the same value as f of x3. So this portion is exactly similar to the one we discussed in differences and divided differences. Now let's come to this one. Changes are here. First, divided differences. This is f of z2 minus f of z1 divided by z2 minus z1. In other words, f of x1 minus f of x1 divided by x1 minus x1, which is 0 by 0 form. We are in trouble. And that's the reason Hermite interpolation technique replaced this value by the derivative of the function at x is equal to x1. Why? I discussed this in the lecture of the Hermite interpolation. Okay, why this idea has been used. Similarly, if you come to this one, f of z4 minus f of z3, f of z4 minus f of z3, you can see f of x2 minus f of x2 divided by z4 minus z3 x2 minus. Again, you are getting 0 by 0. And that's the reason this value has been replaced by derivative of the function at x is equal to x2. And similarly, if you look at this value, f of z6 minus f of z5, f of z6 minus f of z5 is f of x3 minus f of x3 divided by z6 minus z5 x3 minus 6. Again, you are getting 0 by 0. When you are getting 0 by 0, that's the reason this value has been replaced by the derivative of the function at x is equal to x3. The rest of the construction of the table is the same as you know already. This was the only change. That's the reason we have another condition. In this case, you can see the value of j is equal to 2. So we are saying else if j is not equal to 1, but if j is equal to 2, and remember, this tells you when you divide this I by 2 and your remainder is 1, then go for this one. Otherwise, skip this portion. So when I say j is equal to 2, this is the case. Now, j is equal to 2, so the value of I is starting from 1 and it reaches up to 2 minus 1 is 1, 6 minus 1 is 5, reaches up to 5. So it will take the value j is equal to 2 dealing with this column. But now it deals with I also. Will take I is equal to 1. When I is 1 and divisor is 2. So remainder is 1. Remainder is when you remainder is 1. So that's the reason it says that take this value f1 2 is equal to dg. If you remember, this was the derivative of the function at x is equal to x1. So it will replace f1 2 by derivative of the function at x is equal to x1. Now in the same column I am, when I is equal to 2, 2 divided by 2, remainder is 0, is complete division, remainder is equal to 0, so it will skip this portion. Will come to this one, and it will come to this one, will compute for you 2 1, f of 2 1 is equal to f of 3 1 minus f of 2 1, f of 3 1 minus f of 2 1, not 0, they are different from 0, divided by z. This is 4 minus 1, 3, z3 minus z2, z3 minus z2, z3 minus z2, x2 minus x1, we don't have the problem. Which will take I is equal to 3, divide 3 by 2, 1 is the remainder, 1 is the remainder, it will use this one. So f of 3 2, derivative of the function I is 3, dg of 3, and you know that dg of 3 is the derivative of the function at x is equal to x2, it matches with that one. And then it will come to I is equal to 4, 4 divided by 2, complete division, the remainder is 0, so it will not use this idea, it will switch to this one, and it will see that f4 2 is equal to f5 1 minus f4 1, f5 1 minus f4 1 divided by this is 3 plus 2 is 5, 5 minus 1 is 4. And this is a 4 plus 2 is 6, 6 minus 1 is 5, z5 minus z4. So you can see z5 minus z4. Z5 minus z4, x3 minus x2, so we don't have the problem over there. Then it will take I is equal to 5. I is equal to 5. Remember, j is 2. I is equal to 5. 5 divided by 2. Remainder is 1. It will come to this one. And we'll say 5, 2 for you, dg of 5. And dg of 5 was the derivative of the function at x is equal to x3. This is the construction of this column, which is the second column of this table. Forget about this one. Similarly, rest is the same. I will just go for this one. J is equal to 3. J is equal to 3. So 3 minus 1 is 2. 6 minus 2 is 4. So you can see you are reaching up to I starting from 1 reaching up to 4. J is equal to 3. We'll skip this portion. J is equal to 3. We'll skip this portion. Every straightforward will come over here. I is equal to 1 and J is equal to 3. So 3 minus 1 is 2. 6 minus 2 is 4. You can see you are reaching up to 4. F of 1, 3. F of 2, 2. Minus f of 1, 2. F of 2, 2 minus f of 1, 2 divided by, this is a 1 plus 3 is equal to 4. 4 minus 1 is equal to 3. Z3 minus Z1. Z3 minus Z1. This is a Z3 minus Z1. And this is the definition of the divided differences. So I will leave rest for you because I discussed that in the previous. Now let's come to the case, the last one. F of 1, 6. 1, 6, this condition is not satisfied. We'll skip this one. This condition is not satisfied. We'll skip this one. We'll come to this one. I is starting from, this is j is equal to 6. 6 minus 1 is 5. So 6 minus 5 is equal to 1. The I is starting from 1 up to 1. It will come to this one. F of 1, 6 is equal to f of 2, 5 minus f of 1, 5. F of 2, 5 minus f of 1, 5 divided by, let's come to this one. I is 1, j is equal to 6. The 7 minus 1 is 5. 7 minus 1 is 6 minus z1. So you can see that z6 is x3 and z1 is x1. So we don't have the problem. So this loop generates the divided differences table which we need in the Hermite interpolation. I think it will be clear. In case of any doubt, please fill the form and I will try to respond to your queries. My suggestion will be use the MATLAB software. Construct the divided differences table yourself and then use the code which I discussed with you and see that both should match. How to generate this one? This is the first column. This was from the first loop, this was from the second loop, and the rest of the entries are coming from this loop. And how to find out the polynomial, I'm sure that you listen to the lecture which I discussed before, under the topic of Hermite interpolation, forward, backward, and then you can do the interpolation. I'm sure that you will listen to this very carefully and will implement this yourself and will see the outcomes. In case of any queries, please fill the form which I'm sending to you, and I will try to answer to your queries. Thank you very much.